High in the rain-soaked hills of northeast India, in one of the wettest places on Earth, there are bridges that were never built. They were grown. In the state of Meghalaya, where monsoon rains can dump more than 11,000 millimeters of water in a single year, conventional infrastructure does not last long. Steel rusts, concrete cracks, timber rots, flash floods erase roads overnight. Yet deep within the Khasi and Jaintia hills, there are suspension bridges that have endured for centuries, not by resisting nature, but by cooperating with it. These are the living root bridges. They are not relics of a lost civilization. They are not abandoned monuments. They are active, load-bearing transport systems that grow stronger over time because they are alive. To understand how radical that is, we need to look at where they exist. In villages near Cherrapunji and Mawsynram, rainfall is not an event but a season that dominates life. Rivers swell into torrents. Slopes collapse into mud. Footpaths vanish under landslides. In such an environment, the idea of building a static bridge from dead materials is almost naive. The indigenous Khasi people solved this problem centuries ago with a different philosophy of engineering. Instead of imposing structure onto the landscape, they cultivated it. The species at the center of this innovation is the Indian rubber tree, Ficus elastica. This tree sends out long, pliable aerial roots that descend from branches toward the ground in search of stability and moisture. In most places, those roots simply anchor into the soil. In Meghalaya, they are trained, guided, and woven into bridges. This is not myth. It is practiced arboriculture combined with generational planning. The process begins with a young rubber tree planted near a riverbank. Villagers guide its aerial roots across a stream using hollowed-out betel nut trunks or bamboo scaffolding. These temporary supports function like biological conduits, directing the roots exactly where they are needed. As the roots grow longer, they are intertwined, twisted, and braided together. Smaller roots are threaded through larger ones. Stones are sometimes embedded within the developing lattice to provide weight and structural tension. Over time, the roots thicken through secondary growth, fusing into a dense, woody matrix that behaves much like a natural suspension system. Unlike a conventional bridge that deteriorates after completion, a living root bridge improves with age. As the tree continues to photosynthesize and send nutrients through its vascular system, the roots strengthen. They respond to mechanical stress by increasing density in load-bearing areas, much like muscle responding to resistance training. Some of these bridges are estimated to be over 500 years old. They are capable of carrying dozens of people at once. There are even double-decker examples, where one root bridge grows above another, forming a two-tiered structure across deep ravines. If we strip away the romantic language and look at these structures analytically, what we see is bioengineered transport infrastructure. The Khasi are effectively manipulating the growth patterns of Ficus elastica to create tensile structures with self-repair capabilities. The tree remains rooted in soil on either side of the river, drawing water and nutrients continuously. When minor damage occurs, new roots can be guided into weak points. Maintenance is biological, not mechanical. Modern engineers spend enormous resources trying to mimic what these bridges achieve naturally. We develop self-healing concrete infused with bacteria. We experiment with mycelium-based building materials. We research adaptive architecture that responds to environmental load. Yet in Meghalaya, communities have practiced adaptive infrastructure for centuries without laboratories or patents. The philosophical shift is profound. Instead of designing something that resists decay, they cultivate something that metabolizes and grows. In an environment defined by relentless rainfall, oxygen, and microbial activity, steel corrodes rapidly. Concrete absorbs water, leading to cracking and structural fatigue. Timber succumbs to fungi and termites. Every year, maintenance costs accumulate. Living root bridges operate under a different set of physical principles. They are not static objects resisting entropy, they are dynamic organisms participating in it. When the monsoon intensifies, the roots absorb water rather than fracture under it. When soil shifts, the tree's root network adjusts its tension. The bridge is integrated into the ecosystem rather than imposed upon it. This integration also reduces ecological disruption. Conventional bridge construction often requires heavy excavation, machinery, and imported materials. Root bridges are grown from local trees, shaped by hand, and maintained by community stewardship. They represent an infrastructure model that is renewable by design. The most radical element of this system is time. A root bridge cannot be completed in a year. It takes decades to become fully functional. The individual who begins guiding the roots may never see the final structure at its peak strength. This demands a cultural orientation toward long-term thinking that modern development rarely tolerates. In a world driven by quarterly profits and rapid deployment, who invests in a bridge that matures in 30 years? The Khasi did. This intergenerational mindset transforms infrastructure from a commodity into a legacy. The bridge is not just a crossing, it is a symbol of continuity between ancestors and descendants. Maintenance becomes ritual. Knowledge becomes inheritance. The technology survives because it is embedded in culture, not just in manuals. Today, architects and urban planners are increasingly studying biomimicry, which seeks design solutions inspired by natural systems. The living root bridges are not merely inspirational, they are functional precedents. They demonstrate that infrastructure can be self-reinforcing rather than degrading, integrated into ecosystems rather than disruptive, community maintained rather than corporately dependent, adaptable rather than rigid. As climate change increases extreme weather events, many regions face the same challenges that Meghalaya has endured for centuries: flooding, erosion, unstable terrain. Conventional engineering responses often escalate costs and environmental damage. The Khasi approach suggests an alternative paradigm. Grow with the landscape. One of the most famous examples lies near the village of Nongriat. The double-decker root bridge spans a deep valley, with two living pathways layered one above the other. It is not decorative. It is used daily. Tourism now brings thousands of visitors each year, which introduces a new tension. The bridges are resilient, but they are not indestructible. Overexposure risks compacting soil and stressing the trees beyond sustainable limits. This raises a crucial question for modern observers: can living infrastructure survive integration into globalized economies, or does it depend on the slow rhythms of village life? Preservation efforts now attempt to balance access with protection, recognizing that once a root bridge dies, it cannot simply be replaced with a replica overnight. It must be grown again, patiently. The deeper idea extends far beyond Meghalaya. What if we designed coastal defenses using mangrove forests instead of concrete seawalls? What if urban cooling relied on tree canopies and water channels rather than air conditioning grids? What if infrastructure was treated as a living system that required cultivation instead of maintenance contracts? The living root bridges are not an anomaly. They are proof of concept. They reveal that biological materials can outperform industrial ones in certain climates. They show that resilience can emerge from cooperation with ecosystems rather than domination over them. They embody a slower but potentially more sustainable form of technological evolution. When we speak of progress, we often mean faster construction, stronger materials, larger spans. The Khasi model proposes a different metric. Longevity measured in centuries. Strength that increases with age. Repair that happens through growth. In Meghalaya, infrastructure is not assembled from inert components. It is cultivated from living tissue. The bridge breathes. It transports water and nutrients even as it transports people. It binds two riverbanks together biologically, not just mechanically. That changes the definition of what a bridge is. It is not an object placed over a river. It is a relationship between tree, soil, water, and community. Modern engineering prides itself on innovation, yet many of its most urgent challenges revolve around sustainability, resilience, and adaptability. The living root bridges quietly solve these problems using methods refined over centuries. They are not scalable in the industrial sense. You cannot mass-produce them in factories, but they are scalable in principle. The philosophy of growing infrastructure instead of building it can be applied wherever ecology allows. In a time when global supply chains falter and maintenance budgets strain, the idea of infrastructure that feeds itself, repairs itself, and strengthens over time feels almost revolutionary. The bridges of Meghalaya remind us that not all advanced systems require silicon, steel, or software. Some require patience, trees, and the humility to let nature do the engineering. And perhaps the most radical lesson is this: the future of infrastructure may not lie in harder materials, but in living ones. Because sometimes the strongest bridge is the one that is still growing. If you enjoyed this video, don't forget to like and subscribe so we can keep improving the channel. See you next time.